Alright, we are back in section 3.2 talking about independent and mutually exclusive events. So we talked about these a little bit in 3.1, but now we're going to just kind of hit it home a bit here. So two events A and B are independent if the occurrence of event A in a probability experiment does not affect the probability of event B. So they're independent if the probability of one occurring does not affect the probability that the other will occur. And we say that they are dependent if the occurrence of A does affect the probability of B. Okay, so if they do affect each other's probability, they are dependent, and if they don't, then they are independent. So in this example, determine whether the given events are dependent or independent. So for part A, suppose Bucky draws a card from a standard 52 card deck and then rolls a die. The events draw a heart and roll an even number. So the first event, draw a heart, and the second, roll an even number. So the question is, does the probability of one affect the probability of the other? So, if he draws a heart, is that going to affect, what number gets rolled on the die? Or if he does not draw a heart, does that affect what number gets rolled on the die, or vice versa? So this one we can tell hopefully pretty quickly that these two are independent. Right, the card that he draws and the number he rolls on the die, completely independent of each other. There's no way that one of those is going to affect the other. So for part B, suppose two animals live in the same vicinity of the jungle. The events animal 1 survives the year and animal 2 survives the year. So this one is more of an interesting question. Because it's not quite as clear-cut. So, arguments for both sides. The argument for dependent being this statement right here. The fact that they're in the same vicinity means that there could be some interaction between them, right? Or maybe one of them is predator, one is prey. Maybe they're both, fighting for the same food source. So there could be some possible interactions there that result in one animal's survival impacting the other animal's survival. Arguments for independence would be primarily lack of information, right? We don't know what kind of animals they are. They could possibly have no interaction whatsoever, even if they are in the same vicinity. But what we're going to say for this one is we're going to say dependent, again, because the question seems to indicate that because they're in the same vicinity, there's probably some type of overlap there, some sort of effect that they might have on each other. So we'll say it's dependent, but could use more info. Right? If the question said, one of them is predator, one is prey, and they live in the same vicinity of the jungle, then I would say definitely those are dependent. Right? Or if they said, these animals are, one is a bug and one is, a jaguar. And then we might be able to make a stronger case for independent because they would likely have very little to do with each other. So, but we're going to go ahead and use the wording of the question to state that we believe it's dependent. And then we have mutually exclusive events. So mutually exclusive or disjoint events, we talked about last time, have no outcomes in common. Okay, so not the same thing as being independent, just the fact that they have no shared outcomes. So if we look at this example, draw a Venn diagram to show when Satchel draws a heart and a queen. So Satchel was the guy drawing the playing cards from the previous section. We're going to see that guy popping up a lot here. So draw a Venn diagram. So a Venn diagram, if you're a bit rusty, it looks like this. Right, where you have a couple of circles. Oops, mine's a little big. There we go. Couple of circles, and one of them represents one component, one of them represents the other component, and then the middle, that overlap, is where we have any shared values. So in this case, we're looking for drawing a heart and a queen. So our two categories are going to be hearts and queens. So in terms of the hearts, well, every suit has 13 cards in it, right? Going from 2 through 10, then Jack, Queen, King, Ace. I'm going to leave the Queen out for a minute, but we just have 2, 3, 4, 5, 6, 7, 8, 9, 10, Jack, King, and Ace. So we've got 12 elements in there. And then over on the Queen's side, we have a Queen of Diamonds. We have a Queen of Spades. If I can draw anything that even looks kind of like a spade, that would make me happy. That's close enough. That's not horrible. And then, of course, the Queen of Clubs, which the club is going to be kind of like that, almost like a clover. Okay, so Queen of Diamonds, Queen of Spades, Queen of Clubs. And then in this section in the middle, that's going to be where we have a heart and a queen. And there's only one card that fits those two categories. That's the Queen of Hearts. All right, so we've got one card in the middle. It shows that overlap. Okay. So drawing a heart and a queen, not disjoint events, right? Not mutually exclusive because they have a card in common, right? There is a result that is counted in both of those. So we would say these two are not disjoint. Okay. Let's look at an example with tossing a coin. So suppose we toss a fair coin twice. What is the sample space? So the sample space, remember from the last section, is going to be all possible outcomes of this probability experiment. So we toss a fair coin twice. So what could happen? Well, we could get heads and heads again. We could get heads and then tails. We could get tails and then heads. Or we could get tails and then tails. Those are all the possible outcomes. So that's our sample space. What is the sample space, part B, for tossing at most one tail? Okay, well, in this case, we can't toss two tails, right? Only at most one. So we could toss two heads, right? Because that has less than one tail. We could toss heads and then tails, or we could toss tails and then heads. But we could not toss two tails. So then the question, what is the probability of tossing at most one tail? Well, probability of tails being less than or equal to 1. Well, we have 3 possible outcomes where that happens out of the 4 possible occurrences. So we've got a probability of 3/4. And then the question, what is the sample space for tossing more than one tail? Well, there's only one case where we could do that. It's the only case where we would toss two tails. And so what is the probability of tossing more than one tail? Well, that's just going to be this one outcome over all 4 possible occurrences in the sample space. All right. So that's the end of 3.2. So now let's go ahead and move on to section 3.3. So looking at 2 basic rules of probability. So we're going to step it up a little bit, look at what happens when we're given just general events, not necessarily independent events, not necessarily disjoint or mutually exclusive events. So suppose 2 events occurred, A and B. The probability of event B occurring, given that event A already occurred, is represented using this notation. So this over here, that's the probability of B given A. The probability of B given A. In other words, this is the probability that B will occur given that A has already occurred. Okay? And this is called the conditional probability, because it adds a condition, right? A has to occur first, and then we look at the probability of B. If the events are independent, like we've been looking at, and there's no affecting each other's probabilities, then this won't change anything. This would just be the probability of B in that case, right? If A doesn't impact anything in B. But oftentimes we have events that are not independent, so we need to make sure we handle this conditional probability. So let's go back to Bucky's deck of cards and his friend Satchel. What is the probability of Satchel drawing a heart without replacing the card and a spade? Okay, well, to get a heart and a spade, that's going to be the probability of getting a heart times the probability of getting a spade given that he already got a heart. Okay, I'll say that one more time. This is the probability of him drawing a heart times the probability of him drawing a spade given that he already drew a heart. Okay. So, these events are dependent because it said we're not replacing the card. So the probability of getting a heart is 13 out of 52 times the probability of getting a spade. Well, there are 13 spades in the deck still, but because he took the heart out and replaced it and did not replace it, we're left with 51 cards in the deck. So that one's 13 out of 51. So this one simplifies to a fourth times 13 over 51, which as a fraction is 13 over 204. As a decimal, which is a little more informative, we get 0.0637. So the probability of him drawing a heart and then a spade is 0.0637, so about a 6% chance that that will happen. So not very likely. Okay. For the next example, consider this deck of cards. What is the probability of Satchel drawing 2 clubs without replacement? So when we're looking at the probability of 2 clubs, you have to start shifting your mentality a little bit because he's drawing them one at a time. So we need to think about this as 2 separate events. So it's not just the probability of getting 2 clubs, it's the probability of getting a club and then getting another club. So this is the probability of a club and a club. You have to put it in that and form because if we have it in the and form, we can use this formula up here. Okay, so getting that and in there is going to be really helpful in setting this up appropriately. So this is the probability of a club times the probability of getting another club given he already got a club the first time. Okay, so for the first probability of getting a club, there's 13 of them in the deck of 52. Times, now what's the probability that he gets a second club? Well, if he already got a club once, that means that there are only 12 clubs left in the deck, and there are only 51 cards left in the deck. So we're left with 12 out of 51 chance of getting another club. So this simplifies to 1/4 times 12 over 51, which actually simplifies down to 3 over 51, which is approximately 0.0588. So it's even less likely, right? And slightly less likely because one of the clubs is already gone, right? So your odds of getting another one go down. Okay. And then for this next example, in 2005, 19.1% of all murder victims were between the ages of 20 and 24 years old. Also in 2005, 86.9% of murder victims were male, given that the victim was 20 to 24 years old. What is the probability that a randomly selected murder victim in 2005 was a 20 to 24-year-old male? So as you can see, we're keeping it light and fresh here, talking about murder victims back in 2005. So we are looking for the probability that a randomly selected murder victim in 2005 was 20 to 24 years old and male. Okay, so again, if we say a 20 to 24-year-old male, read it as an and statement. So 20 to 24 years old and male. So we're looking for the probability of those two things both occurring. So to find that using our conditional probability, we get the probability that the victim was 20 to 24 years old times the probability that they are male given that they're 20 to 24 years old. And these values, luckily for us, are actually already in the problem. So we know that 19.1% of all murder victims were 20 to 24. So that's the first probability, and remember to convert it into a decimal, so 0.191. Otherwise you're going to get ridiculous numbers if you try to do 19.1. Times the probability that they were male given that they were 20 to 24 years old. And luckily for us, we know that 86.9% of murder victims were male given that the victim was 20 to 24 years old. So that is 0.869. Multiply those two together, we get about 0.166. Okay, so what is the probability that a murder victim in 05 was a 20 to 24-year-old male? About 17%. Okay, so 0.166 probability of this event occurring. Alright. Next up, suppose G-Pod manufactures 100 of their new phones, G-Phone. Because the G-Phone is new to the cell phone market, there is an estimated 15 G-Phones that are defected. I think it's supposed to say defective. Are defective for the 100 manufactured. OG, the creator of G-Phone, decides to test 3 out of the 100 phones. What is the probability at least one of them is defective? Okay, so we want the probability that at least one is defective. Okay. So this is another one like we saw at the very end of the last section. This is another one of those at least one problems. So instead of trying to find the probability of all the possible ways that we could have at least one defective, let's instead look at 1 minus the probability of the opposite of that, the complement, the probability that none are defective. Okay. And if we can find this, then that'll give us the same thing. Just a heads up, I'm going to abbreviate none. Oops, not what I meant. I'm going to write it up here. I'm going to be using the abbreviation ND for not defective. Just as a side note, so I don't have to keep writing out not defective. Okay, so in order for none of them to be defective, we need the first phone that they check, because they're checking 3 out of the 100 phones. The first phone has to be not defective. So the first phone, not defective. Then, and the second one has to be not defective, given that the first one was not defective. And the third one has to be not defective given the first and second one were both also not defective. Which looks like a lot, but once we get the ball rolling here, it's going to go pretty quickly. So we have 1 minus. So the probability that the first one they check is not defective, well, we know that 15 out of the 100 are defective, which means if we're looking for one being not defective, there is an 85 out of 100 chance of that happening, right? 85 non-defective phones. Now for the second one they check. Okay, they're not going to check the first one again, so it's kind of like doing it without replacement. They check the second one. What's the probability that it's also not defective? Well, there are 84 non-defective phones left, right? Because they got one of them already that was not defective the first time. So there's 84 non-defectives left out of the remaining number of phones is 99. Okay, again, because they already checked one of the non-defectives and they took it out. So we're down to 84 out of 99. And then the third one, assuming they already got 2 non-defective phones, there are only 83 non-defectives left to choose, and there are only 98 total phones left. And that's our ugly set of fractions, but it actually works out pretty nicely. We get 0.389 for our value, and that would just be plug and chug through a calculator, right? Scientific calculator. Okay, so we get 0.389. So what are the odds that at least one of the phones they check is defective? There's about a 38-39% chance that at least one of the phones they check would be defective. Okay. So these examples have all been dealing with what happens to an AND probability if we have dependent events. Now we're going to look at the addition rule, and we're looking at the probability of either two events occurring. So now we're looking at an OR probability, so A or B. Well, then we use this formula right here. It's the probability of A plus the probability of B minus the probability of A and B. Okay? And what this does for us, so if the events are disjoint, if they're disjoint, they have no possible overlap, then this value here, the probability of A and B both occurring, is 0. Okay, so if disjoint, probability of A and B is 0. In which case, that would go away, and we'd be left with the definition we saw in 3.1. Right, for determining these OR probabilities. However, if we are dealing with things that are not disjoint, okay, so not mutually exclusive events, then we have to subtract out that overlap. Okay? And what's happening here is we're actually subtracting out a double count. Okay? And I'll show you in this example. So again, we're looking at the deck of cards. He wants his friend Satchel to draw a card. After Satchel draws a card, he puts it back in the deck. Find the probability for Satchel drawing a queen or a spade. So probability of a queen or spade. That's going to be the probability of getting a queen plus the probability of getting a spade minus the probability of getting a queen and a spade. Okay, so that's our setup. So now, the probability of getting a queen, there are 4 of them in the deck of 52 cards. They put the card back, so we have not changed the number of cards, we have not changed the probability. Okay, so This is, now to get a spade, there are 13 out of the 52. And the probability of getting a queen and a spade in one draw, there's only one card that you can do that with. That's the queen of spades, right? That's the only card that is a queen and a spade simultaneously. So we have 1 out of the 52 cards is a queen and a spade. Now, look at these numbers that we just created here. We counted up all the queens, all 4 of them. We counted up all 13 of the spades. So if we had left that last term off, the queen of spades would be counted here, and the queen of spades would have been counted here. So basically we counted that one card twice, right? We counted it as a queen, and we counted it as a spade. So then our probability would be wrong, okay? Because we double counted that card. So by doing it this way, where we subtract off that overlap, we are now getting rid of one card, right? Because the card got counted here and here. It got counted one too many times. So we're taking away one of those 2 times it got counted. And that's what this is designed for, okay? So that when we have when we have events that are not disjoint, okay, then we need to get rid of that double count so that we don't accidentally get an incorrect number. This leaves us with 16 out of 52, which is approximately 0.308. So the probability of him drawing a queen or a spade with replacement is 0.308, so about a 30% chance of this event occurring. Alright, now let's go ahead and move on to section 3.4, looking at contingency tables. So let's revisit the example we did with the left-handed and right-handed people that were taking this study. This type of table is called a contingency table or a two-way table. So each row and column provides information on categories. So a contingency table is a table where 2 categories of data are related. Okay, and this allows us to more easily look at the data and be able to analyze it, including dealing with probabilities. Okay, so let's look at an example. So the following contingency table shows the survival status and demographics of passengers on the ill-fated Titanic. So we're just full of joyful examples today. So we have the category, so we have men, women, boys, and girls, and then survived and died. So we're going to look at some different pieces of information here, but we need to first add up and get some totals, because those are going to help us in our probabilities. So first up, let's get the survived category. So we're going to add up all those numbers, and you get 708. Okay, so 708 people survived. Then in the died row, we have 1,517 people who died. And that gives us a total of 2,225 people. And now going for columns, the number of men on the ship, 1,694. Number of women, 422. Number of boys, 64. Number of girls, 45. Alright, and the total in the corner there is still going to be exactly the same because we're counting the same people, right? Just counting them a different way. So if you add up these 4 numbers, it's going to be the same as adding up those 2 numbers. Alright, so part A, calculate the totals, which we just did. Part B, calculate the probability of a randomly selected individual that is a man which survived. So the probability that we get a man and they survived. Okay, so again, writing it as an and statement. So the probability that a randomly selected person is a man and they survived, that would be this item right here. Right? So that is 334 people out of the 2,225, which is approximately 0.15. So about 15%. So it's not looking too good if you're looking for men that survived. You've got about a 15% chance that any randomly selected person was a man that survived. Calculate the probability that a randomly selected individual is a girl or a boy. So probability of it being a girl or a boy. Well, we have 64 girls and 45 boys, 64 boys and 45 girls. So we're just going to add up the probabilities. So 64 out of the total 2,225 plus 45 out of the 2,225, which is 109 out of 2,225, which is approximately 0.049. So the probability of a randomly selected person being a girl or a boy as opposed to a man and a woman is 0.049. So very few children, as you can see up there, but this just demonstrates it as a probability. It says they made up about a little less than 5% of the total number of people on the ship. Calculate the probability of a randomly selected individual being a woman or died. So probability, woman or died. Okay, now these are not disjoint events, right? Because a person could be a woman and they died, right? So we have to take that into account. So this is going to be the probability of it being a woman plus the probability that the person died minus the overlap, the probability that they were a woman and they died. Because again, if they're a woman and they died, they were counted as a woman and they were counted as a dead passenger, which means that they got double counted. So we need to take away those double counts. So this is going to be, so a woman, there were 422. Let me zoom in on this. So there were 422 women out of the 2,225. The number of people who died was 1,517 out of the 2,225. And then minus the number of women who died, which if you go back and look in the table, was 104 out of 2,225. So you can see it back up in the table there. That was that was this item right there. There's the 104. Okay. Add all of these up. That gives us 1,835 out of 2,225, which is approximately 0.825. Oops, sorry. Came a little close to the edge there. So 0.825. So what is the probability that a randomly selected individual was either a woman or died? About 82.5%. Next up, the probability that a randomly selected individual is a boy given they died. So the probability that they were a boy given that they died. So now we're only looking at the death row. So that's going to be 1,517 people, and there were 35 boys in that group of people who died. So we're looking at 35 out of the 1,517, which is approximately 0.023. Okay, so about 2.3%. The probability that a person is a boy given that they were dead. Okay. And then part F, calculate the probability of a randomly selected two individuals where at least one is a man. So the probability that at least one of the people we select is a man. So again, this is one of those at least one problems. So we're going to take 1 minus the probability that we select no men in our two choices. Okay, so that's going to be 1 minus the probability that the first person is not a man times the probability that the second person is not a man given that the first person was not a man. Okay, so we're coming right up here on the bottom. We got 1 minus, so there were 531 non-men on board out of the total 2,225. Where am I getting that number from? From up here. There were this many men, there were this many non-men. So add up those numbers, right? The 422, 64, and 45. And that'll give you the 531. Times the probability that the second person is not a man, given the first one was not. Well, now there's only 530 non-men out of 2,224 remaining passengers, because we already picked one. This is approximately 0.943. Okay. And remember what we were looking for. We were just kind of going at it using the negation of it. But we were looking, what is the probability that if I select two people on the ship, that at least one of them would be a man? It's about 94%. So really likely that at least one of two people you choose would be a man. Alright, and that brings us to section 3.5. So we're just going to go through this kind of quickly, just another visualization of kind of what's going on here. So looking at tree and Venn diagrams. So we've already talked about Venn diagrams a little bit, but now we're going to also introduce the tree diagram. So a tree diagram is a special type of graph used to determine the outcomes of an experiment. It consists of branches that are labeled with either frequencies or probabilities. So here we have our coin tossing example. Recall that we tossed a coin twice, and you could either get tails, 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 heads, 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 tails. Draw a tree diagram representing this sample space. Find the probability for tossing more than one tail. So, for this tree diagram, I'm going to use my straight lines for this. So we have two choices. We could get heads, or we could get tails. That's the first toss. Once we get to the second toss now, I could have tossed heads and then heads again, or heads and then tails. Or I could have tossed tails first and then heads, or tails and then tails. And this is our tree diagram. So the probability that we tossed more than one tail, if we look at all the possible outcomes after tossing the coin twice, there's only one of them that has more than one tail. So we have 1 out of 4. 1 out of 4 chance of tossing tails twice, or more than once. Okay. So that's how we do our tree diagram. So you go one event at a time, and then look at all the possible outcomes that occur, and then count up how many fit your event's description. And then we get Venn diagrams. So again, we have a few components here. So the universal set is set by a circle. Okay, so we have a universal set, and we're going to draw one in this example. So here's the universal set. This is everything. This is our sample space. And then within that rectangle, we're going to be drawing circles representing different events that occur. okay, or different sets. Overlapping areas indicate elements in common with both sets, so the intersection. So, for this Venn diagram, I'm just going to get it drawn here, and then we'll actually read the question so you can see what we're doing. Okay, so a survey of 200 people are asked, what beverage do you drink in the morning? And offers choices tea only, coffee only, or both coffee and tea. Suppose 20 report tea only, 80 report coffee only, and 40 report both tea and coffee. Okay, and we asked 200 people. Draw a Venn diagram representing beverages people drink in the morning. How many people drink tea in the morning? How many people drink neither tea nor coffee? Okay. So, let's go ahead and get these two here. So there's tea, there's coffee. So how many people drink tea only? That would be 20. How many people drink coffee only? That would be 80. The overlap, the ones that drink both tea and coffee, that was 40. And then the space, the reason we have this rectangle out here is because we surveyed 200 people, but the people who answered tea or coffee or both only add up, if you count them up, that's 140. Which means that there are 60 people who did not select tea, did not select coffee, did not select both tea and coffee. So if we're asking how many people drink tea, well, there's 20 here, and 40 that drink tea and coffee. But we count them because they also drink tea. So that's going to be 60 people that drink tea. And the neither would be everything outside of the Venn diagram. So we would get rid of everything in there and say anybody who doesn't drink those. And we're left with everybody out here, which is also 60 people. Okay, so Venn diagrams can be very useful in organizing information, particularly when you're dealing with possible intersections, right? When looking at whether events are independent, things like that. So that brings us to the end of section 3.5. In the next video, we'll finish up chapter 3 when we get into 3.7. So I will talk with you all once we get into that last section of chapter 3.